Is there a way to remove carbon from the atmosphere and the oceans? What mechanisms are being discussed, and will they work? Hello, friends. Jim here. So let's discuss this. Article appeared in EOS back in mid-December 2023. A transformative carbon sink in the ocean. Water rock reactions in some hydrothermal systems produce both hydrogen, which can be tapped for clean energy, and alkaline solutions that could help draw down atmospheric carbon dioxide. Okay, let's see what's going on. So in this photo, it's shown mixing of naturally vented high pH fluids and seawater at the Lost City hydrothermal field results in the precipitation of dissolved carbonate to form spectacular rock features at the seafloor. That would be the structures indicated here. So this is carbonate, which is chemically written as CO3, that has combined with cations, positive ion, to form these precipitates. Seen here at the base is a 3-story tall, actively venting, they call it IMAX, carbonate tower, as it was photographed during an exhibition to the LCHF in 2005. Okay. Several decades ago, when the concentration of CO2 in the atmosphere was less than 400 parts per million, climate scientists began warning of the negative consequences for Earth's climate of burning fossil fuels. From those early warnings, a consensus emerged that carbon emissions would need to be lowered, eventually zeroed out, to avoid dangerous consequences of global warming, such as extreme heat, stronger storms, more intense floods, and droughts. And we all know that has happened. Not. And so we are seeing things getting very hot, crazy storms, precipitation bombs, floods. We're seeing it. We're living through it now. Today, the atmospheric CO2 concentration is well over 400 parts per million. Let's not even get discussing about CO2 equivalents, which is much, much higher. And of course, it's still rising. Whole pile of research, recent severe weather events, point to the fact that these dangerous consequences are already happening, right? We've been discussing this. Effectively lowering atmospheric carbon levels would require a range of actions, from individuals making hard decisions about lifestyle changes to international cooperation to pursue solutions from a diverse menu of options. Among the options under considerations are methods for deliberate carbon dioxide removal, or CDR, from the atmosphere. Once considered a last resort, is now no longer a last resort. Many approaches to CDR, both on land and at sea, are in various stages of testing and development. Each has upsides and downsides. Well, they're basically talking geoengineering here. And for those of you who follow me for some time, you know overall what my general opinion of geoengineering schemes. They tend not to work. And they tend not to work because of unanticipated interactions, unanticipated parameters, unanticipated problems, and other outcomes. There's just so many variables, so many things that can go wrong. So in this article that we're going to discuss here, they're going to outline a different type of CDR approach that is based on naturally sequestering carbon basically at the sea floor. And that in theory, let's stress, in theory, could remove substantial amounts of atmospheric carbon. Significant questions and concerns would need to be answered about this approach. Okay, at least they are not going into this with the rose-colored glasses, because you hear about a lot of geoengineering schemes, and everyone touts, oh, this is the panacea, this is the fix-all, this will solve everything, blah, 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 and it usually turns into a damp squib, basically. It just falls flat on its face. So the issue here is looking for cost-effective strategies. And typical approaches, store organic carbon and biomass on land and the oceans, efforts to restore natural habitats with capacity for carbon storage are laudable. However, organic carbon is vulnerable to oxidation, which means it gets re-released and it could end up right back into the atmosphere. And look what happens when you have wildfires, right? You're burning carbon, organic material that releases carbon. In the sea, such efforts are pursued through seaweed cultivation, nutrient fertilization. That's a reference to iron seeding, which has not done well. I think one location had perhaps some mixed results, but there was some questions to the data. So carbon dioxide may also be captured by using acid-base chemistry and then sequestered in rock. For example, depleted oil reservoir formations or in the oceans. However, such approaches also run into challenges of achieving permanent storage, raising questions about the security and potential for re-release of sequestered carbon to the atmosphere. And basically, what they're going to be focusing on in this article that we're discussing is base of acid-base chemistry at the bottom of the ocean. Converting CO2 to mineral carbonate affords a mechanism for permanent storage. Key here is mineral. That means you precipitate it. That means you have sequestered it. It is no longer in solution. Okay. Natural reactions known as the Ebelman-Urey reactions, in which silicate minerals such as forsterite, and it's given here basic magnesium silicate, is a type of olivine, react with CO2 to yield carbonate minerals and silica. So here to give you the reaction, so magnesium silicate plus CO2 yields magnesium carbonate, and here's the silica. Okay, so this basically is a precipitate. So in essence, you swap out the silicate for carbonate. So when the carbonate minerals are formed, it's considered to have acted as a planetary thermostat over most of Earth's history because of the dependence on temperature and related feedback. In other words, before we started introducing boatloads of CO2 into the atmosphere, there was a balance. Draw down the CO2, have this reaction, sequester it, eventually, different processes break it down, organisms die, the CO2 is re-released back into the atmosphere, drawn back down again, etc., etc. Well, we've overloaded the system, so now the planet is just running away with the warming and all the other crazy stuff that we see going on. These reactions have, in the past, gradually pulled Earth out of warm greenhouse climates by lowering atmospheric CO2, and they will eventually erase the anthropogenic carbon spike, although not on a timescale relevant to human civilization. That's important to remember. Eventually, yeah. You're going to draw down the CO2 levels, but humans will be extinct long by then. So, in the meantime, humanity may need to implement carbon dioxide removal on a vast scale to compensate for the extraction and combustion of fossil fuels over the past century. Ocean alkalinity enhancement, OAE, in which the addition of ions like magnesium and calcium, sourced from materials such as olivine or lime to the ocean. Calcium would supply the lime, olivine the magnesium. To the ocean drives more dissolution of atmospheric CO2 to form bicarbonate, which is written as HCO3. And this bicarbonate holds considerable promise because the ocean's capacity for storing bicarbonate is ample on the relevant time frame. Indeed, ocean alkalinity enhancement approaches, often involving materials dispersed at the ocean surface, are being studied, though they too face questions about large-scale feasibility. Just like with iron seeding, what was the large-scale feasibility? It wasn't. Are there other marine settings where OAE could be pursued on a broad scale with durable results? Now, bicarbonate is an interesting ion. It can serve as a weak base, especially if it combines with another hydrogen to form hydrogen carbonate, or it could actually serve as a weak acid. It's important, for example, in physiology, it's a buffering system. It helps maintain your blood pH, as an example. So in a lot of physiological processes, it tends to be a weak base, raising pH values. So that's kind of what they're thinking. If we can form a lot more of the bicarbonates and have that in solution in the ocean, we can actually increase the pH of the oceanic water. That's what they're getting at. Transform faults offer a transformative approach. Transformative, okay. Earth's mantle, constituting more than 80% of the planet's volume, is a vast reservoir of ultramafic, which is low silica, rock. In concept, a small fraction of this rock, minimally about 600 cubic kilometers, if completely converted to carbonate, could neutralize the entire industrial age fossil carbon in the atmosphere. In other words, everything humans have pumped into the atmosphere. Oceanic transform faults and their fracture zone extensions present tectonic settings where such reactive mantle rocks, which are typically buried under kilometers of crust, are exposed at Earth's surface. The discovery of transform faults, which connect the divergent plate boundaries located at mid-ocean spreading centers, the mid-oceanic ridges, for example, was key to unleashing the plate tectonic revolution in the 1960s. Now, this goes back to Alfred Wegener, who proposed back in the early 1900s that, geez, if you look at the outlines of the major continents, it kind of looks like they all fit together, and that they must have been together at one point. Everyone thought he was smoking some very interesting herbs, and they told him, "You are silly, how your Earth's a solid surface, solids don't move about, what are you talking about?" Well, it wasn't until later on, in the 1960s, that with the discovery of the mid-oceanic ridge system and witnessing and measuring the seafloor spreading from the rising of basically magma, that a mechanism was proposed for how the continents can move about. And even though Wegener was long dead by then, he was vindicated. So today, the co-occurrence of the right rocks and high relief bathymetry presents an optimal combination of chemical and gravitational disequilibria, suggesting a potential for large-scale CDR found nowhere else on Earth. And then they refer to this figure right here, which we're going to take a look at. So this is a transformative fault. These black lines right here indicating the fault probably slipping past each other. Okay. These little white lines here are the fractures in the rocks. So oceanic transform faults and their fracture zone extensions, right, indicated by these guys here, may be settings where a natural carbon dioxide removal process could be enhanced. In these settings, seawater, pH of 8, indicated here, infiltrates, basically, works its way into the cracks and pores, infiltrates the fractured rock below the seafloor, where it can react with rock, for example, periodotite, that releases thermal mechanical energy and creates alkaline hydrothermal fluids, pH of 10. Okay, and that is indicated by these little white arrows indicating the pH of 10, and then it makes its way into the water. Okay, so they through buoyancy they rise and then precipitate the mineral carbonate when they interact with the seawater back at the sea floor. So because it is, alkaline, is able to remove carbonate and precipitate it out, such as the photos I showed you at the beginning of this video. And so now you have a higher pH and you've sequestered some carbon. So the other thing to keep in mind is that we're at the bottom of the ocean here. There is immense pressure. So oftentimes the immense pressure will decrease precipitation rates. So you would have to overwhelm, supersaturate basically to precipitate out the carbonate. And because of the immense pressure, and in the case of the hydrothermal vents, the extremely high temperature, the immense pressure keeps the water liquid, even though its temperature is well above the boiling point. We call them, superheaters, basically. Superheated water. So then they indicate a little drilling platform, some ship at the surface here. And basically they're sitting there, drilling into the rocks to create more fracture zones, such as indicated with these little gray lines and so forth. That would be serve the purpose of enhancing this whole chemical process. So the resulting hydrothermal fluids might be piped back, and that's these black vertical arrow here, to the surface ocean mix layer, where they can counter ocean acidification and then remove carbon dioxide from the atmosphere. So it's going to precipitate the carbonate at depth, and then you pipe it up to the surface, let it interact with surface waters to reduce the pH, reduce the acidity, increase the pH, thereby hopefully counter acidification of the ocean, which would help corals, for example, reduce perhaps bleaching, and then perhaps also draw down some atmospheric CO2. That's the scheme. Will it work? Well, have to find out, I guess. So the approximate width, length, and height of this diagram, it's not the scale. So we basically have 100 kilometers. 100 kilometers, 400 kilometers, and then just 10 kilometers. So it's basically a 5-to-1 vertical exaggeration, just to show you the process here. So this is not to scale as to what the actual oceanic situation would be. Now, where you have a magma pore slow spreading, typically defined as less than 4 centimeters per year, such plate boundaries, transform fault settings feature relatively fast reacting magnesium silicate minerals in abundance. That's interesting. The scale of transformed fault valley dwarfs that of terrestrial erosional features such as the Grand Canyon. Submarine valley walls are prone to mass wasting, which exposes fresh surfaces of reactive silicate minerals. Locally, the motion of almost horizontal detachment faults results in portions of crust sliding off the underlying mantle, allowing further exposure of ultramafic rock on the sea floor. Active fracturing needed for water rock reactions to yield alkaline solutions is widespread. Slow velocities of seismic waves observed along oceanic transform faults imply that water penetrates to depths of more than 30 kilometers. Because of differential cooling in the seafloor rock in these settings, the fracture zone extensions of transformed plate boundaries also continue to experience differential vertical movement and fresh fracturing. In addition, active faults exposing reactive mantle rock are locally present along ridge crests and along trench walls. Okay, ridge crests, trench walls. Now, okay, most of you are probably familiar with the general mechanism of how continents are moved about. You have magma rising up at the mid-oceanic ridges. You have sea floor spreading, which pushes the plates apart, and then in subduction zones, you have the plates. One plate subducts under another plate, dives under it. In so doing, it's actually pulling some of the oceanic seawater with it. So the result is this whole crust mantle interaction system with the spreading, seafloor spreading, plate spreading, and subduction is actually a way for the planet to filter oceanic water. Because eventually that water will make its way back to the ocean. After it kind of goes through this filtration process for a wee bit. So now, of course, the transformed faults here is a different mechanism as opposed to the mid-oceanic ridges. This is basically sliding, sliding past each other. The mid-oceanic ridges is different. It's a spreading location. Oceanic transformed fault settings are known to host low-temperature hydrothermal systems that sequester dissolved CO2 by precipitating the mineral carbonate. Kind of what we've been driving at during this whole discussion. A prime example, the Lost City hydrothermal field that I referenced earlier in that photo, sits at about 30 degrees north latitude and 15 kilometers west of the mid-Atlantic ridge on the Atlantic Massif. Here, seafloor vents release high pH alkaline fluids. So high pH means that they're in the alkaline fluids. So they have a pH about 10 that react with seawater to precipitate towers over 60 meters tall made of carbonate. For example, calcium carbonate and brucite, which is magnesium hydroxide. So here's some alkaline hydrothermal fluids vent from a structure in the LCHF as seen here. This is the fluid right here and kind of shimmering here. This is a precipitate deposit. Here's the fluid. You can see a little more blurring here. That's the fluid. And it comes out quite forcefully at a really pretty decent rate. So we'll go over the general, chemistry here. Low temperature hydrothermal circulation at the LCHF is linked to the exothermic hydration. Exothermic is a reaction that releases energy of olivine and related minerals by water percolating beneath the seafloor. So, for example, grab a couple of magnesium silicate, grab some water, grab some protons, and voila, you've got this thing here. And this reaction forms serpentine group minerals. For example, this, I guess it's olivine. That's the chemical formula for it, which is the primary minerals in serpentinite rock. The hydrothermal fluids then rise through a permeable system of fractured rock. Mixing of the warm alkaline vent fluids, pH greater than 10, with seawater shifts the carbonate equilibria locally to favor carbonate precipitation. Oftentimes, the pH of a solution will determine whether minerals precipitate or dissolve. If you were to take this chunk of carbonate deposits and bring it into a lower pH situation, this will start dissolving. Which is why I often talk about the CCD being important, that because the calcite compensation depth is the depth at which below the depth carbonate tends to stay in solution. Above it, it can precipitate. Well, the CCD is rising, becoming shallower, which means more and more organisms are finding it difficult to precipitate their shells. Their shells are literally dissolving around them because of the increasing surface ocean acidification. That's also bleaching the corals. So when the CCD goes up, that's bad news for organisms that need a higher pH to make their shells. The CCD is basically, the level at where, it's called a lysocline. Below it, stays in solution. Above it, it can precipitate out. Well, if we start reducing the pH of the surface waters there, you're going to make the CCD shallower and shallower, making it harder and harder for the organisms to make their shells. So, and so why do we have this lysocline? Because in the past, when we had vertical movement, we brought the CO2 to depth. That was also reducing the pH. Now, in local areas where you have this highly alkaline, high pH fluid coming out of the rocks, locally it can precipitate out the carbon into carbonate locally. So what they're trying to say is, can we do this on a much broader scale? That's what they're getting at here. Imagine if it were feasible to enhance this natural CDR process by deliberately expanding low temperature hydrothermal systems and delivering the alkaline fluids to the ocean surface to simultaneously reverse anthropogenic ocean acidification and draw down atmospheric CO2. It may seem audacious and technically demanding, yeah, but the core technologies needed are already available. Okay. So in this little photo here, it said the results of natural carbon dioxide removal are evident in the white veins of mineralized carbonate occurring amid green serpentinite in this rock specimen. So here's the carbonate right here, and all this other green is the serpentinite rocks. Drilling and hydrofracturing at sites of active mass wasting would create fresh reactive mineral surfaces and promote serpentinization, further cracking, and the production of greater volumes of alkaline, high pH hydrothermal fluids. Basically, what we're getting at here in this figure. Drill away, create these fracture zones, and then have this natural occurring reaction take place, release this high pH, greater than 10 alkaline solution, and then grab it and bring it to the surface. That's what they're saying. These fluids can be pumped or directed to rise buoyantly through insulated pipelines to raise the alkalinity of surface ocean mix layer. By comparison with the existing fossil fuel infrastructure that, goes all over the place, piping these fluids to the surface should be eminently doable. As for surface infrastructure, mothballed fleets of aircraft carriers, presumably powered by non-fossil sources of energy, nuclear, might serve as drilling platforms. People are unaware that many, for example, the U.S. naval vessels, submarines, aircraft carriers, they run on nuclear power. Earth's transformed fault scarps cover on the order of about 100,000 square kilometers, an area likely more than sufficient for this approach to CDR. Even if the fundamental technology and scale of exposed mantle materials are available, however, there are practical scientific questions to address. Right. Now, this is a big geoengineering scheme. You have to start thinking, what are the pitfalls? For example, additional research would be needed to understand the relative importance of negative and positive feedbacks in low temperature hydrothermal settings. Right? What are the unanticipated consequences? Negative feedbacks might include clogging, where the precipitation of secondary minerals inhibits permeability. Basically, you plug the cracks in the holes. Then water doesn't filter through. And it can't react with the rocks. Positive feedbacks that keep these systems going, meanwhile, are evidenced by both the long lives of vents and the pervasiveness of fractured and altered rock. There are also potential kinetic issues to contend with. Although the chemistry favors increased consumption of CO2 in the ocean, the pace of the reactions may be too slow to matter on human timelines. So several options have been explored to accelerate the rates of CO2 consuming reactions. For example, perhaps you have the rate of olivine carbonation increases a millionfold above typical rates at the optimal reaction temperature of 185 C and high partial pressures of CO2. Remember, I just said earlier, the pressure at depth is so great that even superheated water remains liquid, even though it's well above its boiling point because of the high pressure. So the high pressure keeps it liquid. Electrochemical strategies to accelerate the process have been explored. And now, what do we have? Oh, yes, the trouble with methane. Gee, figured that was going to show up somewhere, right? Beyond questions of its technical feasibility, the notion of intentionally expanding hydrothermal systems and piping fluids to the ocean surface raises distinct concerns. High on the list is methane, a potent greenhouse, right? Well, we know that. What role do carbon-free minerals play in the formation of carbon-rich methane? Now, I give this article credit for not, for pointing out the flaws to the idea. Not just saying, oh yeah, we found the solution to solve all our problems. No. So they're at least trying. In serpentinization reactions, mantle olivine, a solid solution of typically 90% forsterite, which we discussed earlier, which is magnesium silicate, and 10% phthalate, which is iron silicate, releases reduced iron Fe2+, which is the culprit. Okay. Water oxidizes the reduced iron, forming molecular hydrogen in the process. So you get three, iron silicate plus water gives you iron oxide and silicate and hydrogen gas. Now, iron occurs in two valence states. You have Fe2 positive, which is indicated here. That's ferrous. Ferric is Fe3 positive. So iron with a charge of 3 positive gets reduced to iron with a charge of 2 positive. We see something similar with copper. You have cuprous and cupric. Cuprous is +1, cupric is +2. And same thing with stannous and stannic, with the kind of an old nomenclature approach to naming compounds. But so the reduced iron is Fe2. It's reduced from Fe3, 3+. That's what they're getting at there. So this hydrogen that results from this reaction converts any oxidized carbon, for example CO2, to methane, as indicated by this chemical reaction. And this, by the way, is, if you take the reaction the other way, is kind of what happens in the atmosphere. Remember, water vapor is greenhouse gas. So it would clearly be undesirable to create or enlarge methane sources and have the gas end up in the atmosphere. Gee, that's an example of an oopsie, an unintended consequence. However, hydrogen and methane are gases of energy sources. So if you could capture those gases, you could presumably meet energy demands, possibly quote-unquote clean energy, although burning methane is not clean energy. And in turn, you'd be able to finance more CDR infrastructure. Of course, harvesting these gases would be extremely challenging. Understatement. At Lost City, the carbonate capping rock at the seafloor helps to focus the flow of venting fluids. Whether an artificial infrastructure would similarly focus the gases produced without excessive leakage is an open question. I like this next section. What else could go wrong? Other concerns, apart from the potential escape of excess methane, exist as well. Low temperature hydrothermal systems stand in sharp contrast to high temperature hydrothermal systems, which are common along mid-ocean ridges and hydrothermal vents. The high temperature system, which dissolves magnesium, is in effect traded for protons, vent acidic solutions that subtract from the ocean's alkalinity budget. And here we have it. There's more of the ridge system, right, than there is of the transformative fault systems. There's more of it. So if they subtract from the ocean's alkalinity budget, that means they're increasing the ocean's acidic budget. So universally increasing fluid fluxes from these systems would be counterproductive. Proximity to sites of high heat flow is to be avoided. Yeah, so what did I say here earlier? That this Lost City hydrothermal field sits at 30 degrees north latitude and is 15 kilometers west of the mid-Atlantic ridge. So they're talking here that proximity to sites to be avoided. What is considered too close? Is 15 kilometers too close? What would be you have to then look at the movement of water. What are the horizontal and vertical advection? What are the mixing rates? How are they mixed? So you have to look at all of that. It's not just a simple matter of drill a bunch of holes, suck out the high alkaline stuff, pump it to the surface, and we have the problem solved. There's so many other things that have to be carefully studied, modeled, investigated, and get clear data on. Drilling above fault scarps could conceivably trigger mass wasting events and tsunamis. Lovely. A potential hazard that has been studied in tectonically active regions such as the Puerto Rico Trench, which is right there in the Caribbean. When I was in St. Croix, I spent a semester there studying marine sciences. I was scuba diving off the Cane Bay wall, and I was at about 120 foot depth and about 400 yards from where the wall just suddenly, about 400 yards away from the wall face, where that wall face just dives down into the Puerto Rican Trench. I literally had about minimum of 14,000 feet underneath my flippers. And there I was hanging out there. I had my buoyancy adjusted just right. That wasn't sinking or rising. Yeah, it was kind of cool. I was looking at the black coral that was on the wall face. But yeah, pretty wild area there. There's a big Puerto Rican trench there in the Caribbean. Activities associated with the proposed CDR approach could also disrupt seafloor and ocean surface habitats. Yes. Such disruption is a major concern with seafloor mining efforts, including mining methane hydrates. And substantial efforts would be required to avoid damaging seafloor ecosystems just because you want to do CDR. To minimize disruption in surface ocean habitats, a delivery system could be engineered to remove problematic solutes and to dilute the alkaline vent fluids before they were mixed with surface waters. Well, if the whole point is to raise pH, it all depends, I guess, at how much you want to raise the pH. Dispelling a wicked problem. Must be a New Englander. Wicked cool, wicked smart, wicked awesome. The Pandora's box of fossil energy has created the wicked problem of climate change, which has no simple single solution. Yes, exactly. There's going to be any geoengineering scheme is going to have unforeseen problems, unforeseen interactions, unforeseen results, unforeseen parameters. Yeah, we're moving away from fossil energy sources, but even if carbon emissions disappear tomorrow, an excess of CO2 would long remain in our skies, which is what I've been saying for how long, especially as ocean temperatures are rising. You're going to outgas the CO2 in the oceans? So no perfect options for removing excess carbon exist. Let's highlight that because they're correct. No perfect options for removing excess carbon exist. Every geoengineering scheme has its issues. All methods face questions over their safety, durability, and efficacy at large scale. Yeah, what goes on at that field that they're talking about here, right? It's local. How are you going to do this on a global? You go to that little place there, okay? How are you going to get that distributed to all the surface waters in the oceans? The natural CDR process that occurs at oceanic transform fault settings, if it could be harnessed to draw down atmospheric CO2 and raise surface ocean pH, represent a potentially transformative solution. These settings combine optimal chemical and gravitational disequilibria at the scale needed. The right rocks, ready to fracture are present in effectively unlimited quantity. Careful with the use of the word unlimited. Nothing is unlimited. If reduced gases like hydrogen and methane could be harvested for energy without fear of leakage, the approach could be financially sustainable. But would it achieve the desired results? Here we have geoengineering solutions they do have unintended consequences. So a cautious approach is in order. So we say more research is needed to investigate this before starting to think of going full hog on this. A system of governance to monitor, regulate research, testing, development is also needed. So, is this planet saving? Well, we're doing great damage to the planet. There's no doubting about that. We're causing mass extinction, no doubting that. Is it planet saving? Well, Earth is going through cycles. It's had ice ages. It's had hot house Earth. It's had high levels of CO2, low levels of CO2. It's had, acidic oceans, not so acidic oceans. What the question should be is this human civilization saving? And, as noted earlier in this, it might do the trick, but not on human timescale. It's a very interesting idea. The concepts, the principles seem reasonable. I wonder about the practicality of it. I don't think it's practical because the oceans are a big place. Just like my criticisms of iron seeding. The criticism of most geoengineering scheme. Including, the one about, putting aerosols in the atmosphere. Sulfate aerosol injection. We have put there's so much thermal inertia in the system that any of these schemes, it may have some local benefits, but globally, I am skeptical. And again, we need to be cautious of the unforeseen parameters, unforeseen interactions, unintended consequences. They touched upon it here with the methane and the hydrogen and the difference between the transform faults and the mid-oceanic ridges and so forth. Low temperature hydrothermal events, high temperature hydrothermal events. They touched upon that. So I give them credit for bringing those points up. But for the scale that is needed, as I said, I am skeptical. And will CO2 levels decrease? Will ocean acidity decrease, i.e. the pH rises, becomes less acidic? Sure. About a millennia or two, at least, not longer. It's just that we did so much damage in such a short time. That's the problem. You are not going to be able to undo close to 300 years of one big geoengineering experiment in a decade or two. You're just not going to undo it. So, as you know, I typically tend to be extremely skeptical of geoengineering schemes. I think they're, of course, I'm not an engineer, but my understanding of physics and thermodynamics informs me that most of it's probably not going to work. But I put this out there. We folks who consider and mull it over. You might have a different take on it, what have you. But as I said, the principles sound reasonable. I am extremely doubtful and skeptical about the feasibility to have any significant, noticeable impacts. So, thank you for your time. And, be sure to give this video a like. Leave comments. Both of those actions help promote this channel. And until next time. If you stuck around to the end of the video, thank you for watching. Be sure to give this a thumbs up as it really helps the channel. And if you can, please support me either on Patreon and or buy me a coffee. Details in the description box below. Thank you.